Welcome, everyone. My name is Jasper from the Kreeke. As you've just heard, I'm a finishing PhD student of Raf Bocklandt. And in my PhD, I've been proving some deformed mirror symmetry for punctured surfaces. And today I'm here to report on the A side of this, so deformations of, in our case, A-infinity gentle algebras. Now, before I present the agenda for today, I want to briefly recall some background, the general ideas of what I've been thinking about. So the first item is Fukaya categories, right? So the idea is you start with a symplectic manifold and you try to construct a Fukaya category from it. The objects of this Fukaya category would be the Lagrangian submanifolds of X, and the home spaces would be spanned by intersection points between them. The higher product of this A-infinity structure would be given by disks between the Lagrangian submanifolds. And that's basically the idea you want to follow. But that's actually very hard. So this is all like the way I'm saying this here is very much of a folklore statement. It's super hard to define because of the reason that you might know, namely if you have Lagrangian submanifolds which are not transversal, then if you just take intersections, you will have infinitely many points, which you typically don't want. So this is extremely hard to find, to define in general, and that's why you sometimes try to find easier models to do this. Why do I go into Fukaya categories? Because I want to do some mirror symmetry. Well, I've been instructed for this talk to spare you the symplectic side a lot. But just as a background, I want to say, so folklore statement of mirror symmetry is that you want to have a symplectic manifold X and a so-called mirror manifold, which is algebraic variety X check, and you want that Fukaya category of X is the coherent sheaves of the other. You typically want to achieve this on the A-infinity level. And well, for me, mirror symmetry is just any functor, any A-infinity functor from one side to the other. Any questions? No, there was nothing. Okay, thanks. Yeah, so if that is mirror symmetry, well, there's another component I want to bring into the story, which is deformation theory. Deformations, what is deformations? So you can do deformations of lots of objects, algebras, variety schemes, that's all kind of existing stuff. You can define over algebraic rings, you can, so polynomial rings, think, you can define deform over local rings, you can define over a scheme instead of a ring. So formal deformation theory is a little special. Formal deformation theory is not the same as deformations over local rings. Formal deformation theory is when you work with a completed tensor product. So if you remember, like deformations of schemes typically involves that you take the ordinary pullback or cross product of schemes, and in this case you really want the completed tensor product. And if you get into this world, you're really like doing algebraic deformations over some local ring, and this is nowadays best studied in terms of DGLA. So that's why DGLA study comes in. So DGLA algebras, if you know them. I will talk about this in more detail later, of course. So natural question here is, once you have mirror symmetry, can you deform mirror symmetry in any sense? So if we start with some X and we have a mirror X check, and we now pick some deformation, let's call it, I will always call these deformations, I will index them by letter Q. So deformation XQ. Is there also a deformation of X check in any sense? So a deformation of the algebraic structure in this case, so that the derived categories, so the Fukaya category on one side still stays isomorphic to the coherent sheaves on the other side. And this is the question for me behind deformed mirror symmetry. Okay, so if you think deformed mirror symmetry, maybe we can make a little more concise. So what kind of deformations would we be interested in on the Fukaya side, right? So the Fukaya side is a bit what I'll be talking about today, special case of gentle algebras. so for punctured surfaces. Are there known deformations of Fukaya categories? And the answer is yes. So Seidel in 2001, Seidel, who is one of the great men behind making Fukaya categories rigorous, he introduced the idea of taking a Fukaya category relative to a divisor in X. So if X is a surface for me, which means a real surface, so think one complex dimensional to real dimensional. If X is a surface, it just means D is 0 dimensional. So in this case, punctures, right? You pick out a finite set of points from your surface. This is the if you follow Seidel's vision from 2001, should give you a deformation of the Fukaya category of X of the surface over the power series ring in one variable. So Seidel in 2001 wrote down how this should happen, but only 20 years later, it was actually this construction was apparently finished. So I found this recently. So Sheridan and Perutz did this extremely hard again. And basically in the talk today, you will see something like a version of this construction in case of punctured surfaces. Very algebraic, very elementary. You can capture the deformation very explicitly. Okay, that said, so what news are we going to see today? So I will present on 3 quests, I will call them. So our first quest for today is to comment on A-infinity gentle algebras, explain a little how they model Fukaya categories, and write down one specific deformation of such an A-infinity gentle algebra, which tries to make Seidel's 2001 vision true. In the second quest for today, I will pick an arbitrary A-infinity gentle algebra of an arbitrary punctured surface and classify the entire deformation theory. So the entire A-infinity deformation theory it has. Related to that, I will also explain why this deformation problem is formal. So the DGLA involved here is formal, which means it's L-infinity. It has an L-infinity model with vanishing higher brackets. In the third quest for today, I will relate a bit to work of Severin Barmeier, Wang, and Barmeier-Schroll, I think some of whom are here and I have met in advance. And the idea is a bit to explain again. So what is the difference? What is the difference between the different types of marked surfaces? One kind of marked surface are the punctured surfaces, which we study today. And the other kind of marked surfaces is basically the ones which Barmeier-Schroll-Wang are studying. So their story runs entirely in parallel. Yeah, and we found that we both are looking at the deformation theory of these things. I am on the one side for the punctured surface case, and Barmeier-Schroll-Wang are on the other side. And I briefly want to relate at the end of my talk, to that. Okay, and yeah, if I still have a few minutes left, I can say something about some other stuff in my PhD thesis, namely something I will comment a bit on this deformed mirror symmetry thing. So how you can get your deformation of this gentle algebra to the B side. So really see something like the deformed gentle algebras in action. So from a language perspective, what are we going to learn today? Well, A-infinity gentle algebras, so gentle algebras of punctured surfaces together with their natural A-infinity structure, some A-infinity deformation theory, and how to build A-infinity or L-infinity minimal models. Maybe I see a lot of you actually have their camera off. But it would be great to know, so who of you is actually an expert or knows a lot about A infinity deformation theory? Raise your hand. I see one hand here. Maybe, see, someone? Okay. Who of you guys knows a lot about, let's say, Hochschild cohomology, formality, minimal models, this kind of thing? Raise your hand. A few people, cool, okay. Yes, nice. Okay. Okay, so what are we not going to learn today? So as I said, we're not going to dive into any symplectic theory. We are instead in the punctured surface case. So this is completely algebraic. You don't need the symplectic volume form at all. You will not see any higher dimensional theory. And I'm not going to say anything. I mean, not really on the coherent sheaf side. Maybe in the deformed mirror symmetry, I can briefly say something about the case of mirror symmetry for punctured surfaces. So I'll basically, I'm not here. I cannot teach you any mirror symmetry in this sense today. Okay. So this gives rise to the following agenda. For quest 1, I will say something about A infinity categories. I will introduce A infinity gentle algebras, A infinity deformations in a naive way, and I'll write down this one specific deformation which aims at making true Seidel's vision. In the second quest, we'll do A infinity deformations more thoroughly by looking at the Hochschild DGLA and classify the entire deformation theory. In the third quest, I will just say, okay, what other gentle algebras are there? So coming from other types of marked surfaces, and relate to Barmeier-Schroll-Wang. And in the outlook, if I still have time, I can say something about deformed mirror symmetry. Now, this talk also has an appendix on mirror symmetry on DGLA level, where I sketch how to do some of the ideas of today, which are a bit naive, how to do these ideas on the DGLA level, so an L infinity level, which is just a bit better so a bit more powerful. And but I'll probably not present this appendix today. Let's get started with quest 1, A infinity categories. So A infinity categories, as you know, are better than triangulated categories. They are a bit more liberal than the G categories. And in their idea, they are equivalent to K-linear stable infinity categories. So yeah, everyone who does this kind of theory is free to choose from 2 kinds of languages, which to approach the same kind of things. Now, A infinity categories, what is an A infinity category? An A infinity category is a set of objects together with graded Hom spaces. So the Hom spaces are supposed to be graded vector spaces over a field together with higher products. So you're not only going to have one composition, you're going to have higher compositions for every k greater or equal 1. Yeah, I've basically written down here how these maps should look like. The tensor product basically just means like your maps mu k are supposed to be multilinear. And what are these maps mu k supposed to satisfy? They're supposed to satisfy the A infinity relations, which I've written down here. Now, a few days ago, I benchmarked my talk with a few colleagues at work, and they said, Jasper, you really need to write down some trees in this case. So how does this axiom look like? This axiom looks like if you pick an arbitrary sequence compatible sequence of input morphisms, and you sum over all possible ways to insert some subsequence of them into mu, and all the remaining elements and this mu again into mu, and you sum over this, you're supposed to get 0. Yeah, so taking this kind of trees, yeah, so and this kind of sums is always at the heart of A infinity studies. Okay, what did I not say here? The degree of mu k is supposed to be 2 minus k. right? Because I mean, the Hom spaces have an internal grading, and the degree of mu is supposed to be 2 minus k with respect to this degree. The G categories are the special case where all higher products vanish, so you only have differential mu1 and mu2 a product. Now, why is this so? Why is this the case? If you write down the first few equations for the first few A infinity relations, right? If you just have one input A1, what you get is mu of A1 is 0. So mu1 is supposed to be a differential. And for example, the second one would read mu1 of mu2 A2 A1 plus, and you can imagine how this continues here. So we do get mu2 of A1, mu1 of mu2 A1 plus mu2 of mu1 A2 A1 is 0. And raise your hand if you recognize this relation somehow. Who of you recognizes this? No one recognizes this. I suppose some people here recognize this. Okay, so this is the this is just the Leibniz rule for mu1 combined with mu2. So it says that mu1 should be a derivation with respect to the product mu2. Let me briefly see. There are some messages in the chat. Is there anything important? No. Okay, there's no questions here. Okay, yeah, so why do you study A infinity categories in mirror symmetry? Because the objects that go in their Fukaya categories and coherent sheaves, those are naturally A infinity categories. Yeah, so gentle algebras. Where do gentle algebras come from? What are they? Why do we do this? Gentle algebras are an old thing. Gentle algebras have originally been introduced as associative algebras. And I think some 10 years ago, so my supervisor had the idea of adding some A infinity structure to them to make them reflect the topological structure of surfaces. And the idea was to build a discrete model for wrapped Fukaya categories in order to be able to work better with wrapped Fukaya categories of surfaces. Then 2014, I think Haydn, Katsarkov, and Kontsevich in their famous paper generalized this still a bit. So they allowed for more liberal types of arc systems. And nowadays we can say, I think gentle algebras are a standard model for wrapped Fukaya categories of punctured surfaces and other kinds of marked surfaces. So our focus today will be on, in the language of Haydn, Katsarkov, Kontsevich, will be to look at closed surfaces with punctures. So in where all boundary components are circles S1, which are fully marked. So what you see here is that the marking I've drawn here in black. And so we are not going to look at other kinds of marked surfaces where the boundary might also be where the boundary is divided into alternatingly marked and not marked intervals. Yeah? So these are also called marked. These are also marked surfaces, but we are not going to study them today. We are instead going to focus on punctured surfaces, so where the boundary components are fully marked as ones. So yes, so let us define this these kind of marked these punctured surfaces and their gentle algebras. The starting point for the whole definition is to choose an orientable closed surface together with a finite set of punctures. For example, I've drawn here a sphere S2 with 6 punctures. So this is the 6 punctured sphere. And what you need in order to define a gentle algebra from this is you choose an arc system. So you choose arcs between the punctures. So an arc runs from a puncture to another puncture. arcs that split the surface into polygons. So for instance, I've drawn here 6 arcs, so from which run between the punctures, and they divide the sphere into 2 parts, one front side and one rear side. So this we call the polygons. So both are in this case 6-gons. Now another famous example is the 3-punctured sphere. The 3-punctured sphere is also, if you regard it as lying on the A side of mirror symmetry, the 3-punctured sphere is known as the pair of pans. Okay, so if you start with an, if you have an arc system given, we shall so a punctured surface together with an arc system. We shall define from it gentle algebra. Maybe one piece of notation before we get started. So I tend to use the letter Q for this. Why do I use Q? Because it is it looks like a quiver, right? So what are the vertices? The vertices of Q are the punctures, and the arrows in Q are the arcs between the punctures, right? So I imagine my my arc system as a quiver embedded in the surface. So I always start from Q, and I will denote gentle algebras. I will denote them ultimately by GTLQ. Okay, so gentle algebras, despite their name, are actually categories. You can also view them as algebras, infinity algebras, but they have a lot of idempotence, which makes it just nice to view them as categories. Their objects are the arcs, right? So for every arc in my arc system, I view this arc as an object in the category, and the hum spaces are just spanned by the angles between 2 arcs at punctures, right? So if 2 arcs come together in one puncture, you look at all possible angles. So for in this case, here's a puncture, and A and B are coming together here, and there's an angle between them. Of course, there's also a longer angle. So for example, this one is also an element of the hum space, and the whole hum space is spanned freely by these kind of things. And why do you do this? So you might think now, okay, so gentle algebra is not gentle because it's not finite dimensional. You're fully right. So this is not, in a sense, not classical gentle algebra, but it's the best we can do. In particular, we need these infinite dimensional hum space because we want to model wrapped Fukaya categories. And wrapped Fukaya categories, as you know, they have infinite dimensional hum spaces because of the wrapping around the punctures. Okay, so these are the objects and hum spaces of GTLQ. What is the product? So classical product. So you might know this. So if we have a puncture here and we have a few incident angles, and one angle stops where the other angle starts, then they compose to the composition angle, right? So alpha and beta just compose to this angle. In case alpha starts somewhere else than where beta ends, for instance, in this case, this is part of maybe some polygon, right? And alpha and beta are the internal angles of this polygon. They compose to 0. And yeah, in this sense, if you up until now, this is very much like gentle algebra in the classical sense of 35 years ago. Yeah, so as I announced, we wanted to put some A-infinity structure on this, which is nowadays really regarded as an essential part of the gentle algebra. So never study gentle algebras, these gentle algebras of punctured surfaces without. So what you do is you add a higher product for every immersed disk. What this means, so what is an immersed disk? An immersed disk means you stitch together a bunch of polygons. Remember that a gentle algebra, so GTLQ here is a combinatorial gadget. So you have polygons and you can stitch multiple polygons together. And so whenever you have a sequence of angles which runs around one polygon or multiple polygons, as I've drawn here, then you get a higher product. For instance, here the mu6, this is just an elementary polygon. The mu6 of this sequence is simply the identity of the arc A where you started, for instance. And you can, as I said, you can also stitch together multiple polygons. For instance, this sequence here has a mu5, and it's the first angle, or the last angle, is allowed to come from or to leave into outside of the immersed disk. So, for instance, the first angle here comes from outside, and the result is this angle I've drawn here in red. So this is the way that the A-infinity products work for GTLQ. What is important to realize here is you're not supposed to cover punctures. So if you have multiple polygons stitched together, and in the middle there's a puncture, and you draw all these angles around here, the higher product of those is simply 0 because there is a puncture in the middle. Okay, so what's the spirit of gentle algebras? Why do we do this stuff? The idea was to model the Raf-Fukaya category, but are they actually equal? And Abu Zaid in 2011 showed in a 1.5-page proof that this is indeed the case. What was his idea? He said, okay, so we are going to look at the Hom spaces in the Raf-Fukaya category, and you might know this Raf-Fukaya categories are somehow like you have to put a lot of effort to make the A-infinity structure work at these wrappings, because somehow you have to introduce this continuation map. So this blows up your Hom spaces hugely, while the gentle algebra just has very small Hom spaces in comparison, like one angle. It has a differential, then I think maybe a thing I didn't say, right? Differential on GTLQ is supposed to be 0. How do you put this 0? So GTLQ itself has vanishing differential, while the Raf-Fukaya category has this a huge Hom space and some differential. So Abu Zaid just shows that in the case, if you restrict to an arc system, you just look at arcs inside of the Raf-Fukaya category, you can kick out the continuation map and obtain just an embedding in this case. So and all the other objects in the Raf-Fukaya category, so for example, closed Lagrangians you can make by stitching together arcs. Now, on our first quest, I wanted to talk about the construction of A-infinity gentle algebras, which I have now said something about, but we also wanted to deform these things. So what is an A-infinity deformation? Let us just give more or less a slightly naive definition here. So the starting point is an A-infinity category, C together with its product mu. And the idea is to change mu infinitesimally. So you work over some local ring, and you deform the product mu such that it still satisfies the A-infinity relations. Now, some of you may know that just doing this procedure is not good enough from a perspective of the deformations via the DGLA. And what you actually have to, or what you should allow, is also to allow some infinitesimal curvature to come in. So this means that for every, you should not only allow products mu k for k greater equal to 1, but we should also now start allowing mu 0, a so-called curvature, which is supposed to lie in the infinitesimal two-graded part of the endomorphism space of every object x in your category. So for every x, you are allowed to choose some infinitesimal curvature. And the A-infinity relations, or the rather curved A-infinity relations you ought to satisfy, are the same as the A-infinity relations, only that you allow the inner mu k to be possibly also mu 0. So for instance, the relations then read that the mu1 applied to the curvature is 0, and mu1q is not a differential anymore. but instead it squares to commuting with the curvature. Okay, so these are A infinity deformations. So yeah, I think with this in mind, I can already start sketching how we want to make true Seidel's vision. So Seidel's vision was that you have Fukaya categories and you can deform them by working relative to a divisor. And we've already seen that in the case of punctured surfaces, the gentle algebra GTLQ is a nice model for the right Fukaya category. So the question is, okay, so can we transport this deformation from the Fukaya category on the gentle algebra? So to understand what this deformation of GTLQ should then look like, let's have a brief look at what Seidel says what should come out, how the A infinity product should get deformed. He says, okay, so if you have a disk which covers a puncture, so you have this is a large disk and there's a puncture in between, and these are intersection points between Lagrangians. So classically in the Fukaya category, you would have vanishing product of these because there's at least where for the portion I've drawn here, there's no disk between those points. But in the relative Fukaya category, so I'm writing the product as mu k here, there is a product and it actually gives Q times T. In this case, T is just this output morphism here, and Q is our name for the deformation parameter. So once you have a disk that covers, you count how much you do not only count disks that don't cover punctures, you also start counting disks that cover punctures, and for every disk you weight it by the power of Q given by, so Q to the intersection index of the disk with the set of punctures. Okay, so if this is the deformation of the Fukaya category that we should study, so what is the deformation of GTLQ? I will define this one. Yeah, how to do this. So what we're going to do is go a little beyond Seidel's deformation space. So Seidel said we do one overall deformation parameter. We'll rather do a deformation parameter for every puncture. And the idea is to define the higher products mu k as also weighted by Q. Of course, we are in the gentle algebra here, so you're not working with closed Lagrangians, but you're working with arcs, right? So here's puncture, 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 and there's arcs between them. So whenever you have kind of immersed disk that now is allowed to cover a puncture, you will get a result. In this case, the deformed higher product mu 6Q of these 6 angles is just Q times the identity of A, wherever A is. If A is here, might be, and alpha 1 starts here, and alpha 6 is this angle. Okay, so this thing, you can try whether this is a curved A infinity relation, A infinity deformation. It is not. What you need is you need to include some curvature. Only if you include curvature, it will become an A infinity deformation. And what curvature do you introduce? Well, let's regard an arc A. Recall that arcs are the objects, so we want to curve the object. So for every arc A, you look at the 2 loops, so the full turn angles at both endpoints of this arc. And the curvature we're going to give this arc is Q times this loop on this side and P times the loop on this side. Remember that we are working over the ring which has as many deformation parameters for every puncture. So for instance, Q and P in this case are simply the generating variables of the local ring. So this expression makes sense. Any questions up until here? there's no questions until now. Let's continue and do more questions later on. Yeah, so who of you would have thought that this is actually the right deformation to make through Seidel's vision? Well, I checked this out, so I can prove that yes, this is the case at least. So I can show that the derived gentle algebra, so this some A infinity language which I'm writing down here, so the derived deformed gentle algebra, which I just defined, agrees with the relative Fukaya category on a large part. The proof is some 50 pages long or so, because what you need to do is what I've written here is you need to compute the minimal model of the twisted completion of this deformed gentle algebra. And that's not so easy, because computing minimal models includes lots of choices, and you have to compute all these trees. I can say something later about that. And yeah, so after computing the minimal model, or after setting up all this thing, I constructed lots of data structures to capture all the resulting terms. There's like a huge amount of data, huge amount of possible products that come from this derived category. So you need to compute the entire A infinity deformation. Imagine how the entire A infinity structure on this deformed derived category, which is like huge. So but finally, through all these data structures, I was able to identify the higher products on this side with disks. So with disks that cover punctures, so essentially with just higher products in the relative Fukaya category. Now, why is this so long? Can't we just do Abu Zaid's 1.5 proof in the 1.5 page proof in the deformed case? There's an issue here. So there is no relative Raf Fukaya category. Remember that Abu Zaid started with an existing model, which he and Seidel had actually constructed. So Abu Zaid started with an existing model of a Raf Fukaya category. But you cannot do this in this case, since there is no relative Raf Fukaya category. So there's nothing we can embed and reduce the structure from. Yeah, why did I say only on large part? I only computed this A infinity structure on that part that I need to perform deform mirror symmetry. So only on the case of so-called zigzag Lagrangians, which you might know. Raise your hand if you know zigzag Lagrangians. Can you briefly scroll through? Okay, there's a lot of people here actually. Raise your hand if you know zigzag Lagrangians, maybe from dimers, or I don't know, maybe if you know the Seidel Lagrangian, that's already an example. So if you know the Seidel Lagrangian in the three punctured sphere, the pair of pans, this is an example actually of a zigzag Lagrangian. And if you know the A infinity structure on the Seidel Lagrangian, then you're able to construct the mirror already. Okay, right. So this is one specific deformation, and we have seen it agrees with the relative Fukaya category. So somehow this finishes our first quest that yes, we've made, at least in part, made through Seidel's vision. My quest too is, yes, there's a question.
There was a question in the chat whether this is Z mod 2Z graded or.
Yes, excellent question. Yes, all the time I've been working with a Z over 2Z graded gentle algebra. Maybe Zhangfang, would you like to elaborate a bit more on your question?
So in your theorem, you have this derived equivalent, right?
Mm-hmm.
But the left-hand side should be Z2 graded, right? Otherwise, maybe it's not well defined.
Yes, excellent question. So what do you think would fail if I go to Z graded?
Yeah, I don't know. I just thought maybe these twisted categories is not well defined. I mean, you have curvature, right? And
the curvature, yes, exactly. Yes, very good. So this is exactly the point. If I go back a little to this curvature here, so this curvature here, this is not going to have degree 2 in general, only if I work z/2z graded. So very well observed, Chanfang. Exactly. I always, yes. So if I look at z-graded gentle algebras with a infinity structure, and I deform that structure, so I will get very chaotic deformation theory. Well, if I only do z-grade, if I start from z-graded as z/2z graded, if I start from only even odd parts in the beginning, I can write down very clear deformation theory. Yes, very good. Thanks for your comment. Let's continue maybe with quest 2 and see what we can finish today. So what is deformation theory? The idea is to pick objects and change their shape, right? So possible objects to deform are schemes, varieties, algebras, everything. Like, I mean, we mathematicians are only restricted by the creativity of our mind. So whatever kind of objects you can think of, you can try to deform them. Parameter spaces you can define over, you can deform over manifolds, algebraic spaces. You can define over formals or local rings. You can try to capture deformations in a family. You can do deformations functors a la Schlesinger. You can capture in DGLAs. Now, methods have improved over time. Please use DGLAs wherever you can, because DGLAs, like in comparison to say just families or deformation functors, if you have the DGLA, you have the higher structure basically. So use DGLAs whenever you can, whenever you are going to compute Hochschild cohomology. Always, please remember to compute the L-infinity structure too. Okay, what are DGLAs? A DGLA is a graded vector space together with a differential and a bracket satisfying Leibniz identity and Jacobi rule. The Hochschild DGLA is a particularly important example of DGLAs. Hochschild DGLAs you might know from associative algebras, but also got extended to the case of infinity algebras and infinity categories. What I've written down here is a bit jargon, so a bit a super abbreviated kind of thing. Your cochains are basically every possible deformation candidates of so everything you might be able to add to your product's mu, including possible curvatures. So that's why there's 0 here. The bracket on this DGLA is the Gerstenhaber bracket, which you just know, and the differential is commuting with the given higher product of C. So the mu is the higher product of C. And this is, in case C is an ordinary algebra, this just boils down to the ordinary Hochschild differential for associative algebras. Raise your hand. Raise your hand if you know this definition in case of A-infinity algebras. Yes, Severin, okay. Anyone else? Can I see any hands here? Anyone? Okay, so yes, this is interesting. I think I've I would like to claim I've never actually seen this definition being written out for A-infinity algebras anywhere in the literature. But there's of course people. There's of course I think there's work getting done on this. Okay, so if L is a DGLA, you can look at the set of Marat-Catin elements over a local ring R. So if R is a local ring, you can take the maxima ideal. You can look at all degree 1 elements, the infinitesimal degree 1 element, which satisfy the Marat-Catin equation. We call this set MCL over R. Why are Marat-Catin elements important? Because the Hochschild, the Marat-Catin elements of the Hochschild DGLA are precisely the A-infinity deformations of C, right? So if you look at a deformation and I split it into the original, the non-deformed part, plus some infinitesimal part I add up, this being satisfying the curve A-infinity relations is just the same as saying that nu, the element nu, is a Marat-Catin element of HC. Why DGLAs? What can you do of nice stuff with DGLAs? You can take minimal models of DGLAs. A minimal model is you basically pass, you kill the differential mu1, you take cohomology, but you don't forget any higher structure. So you will get an L infinity algebra. And what is an L infinity algebra? An L infinity algebra is graded vector space together with differential bracket and higher brackets, right? So this idea is just like as an A infinity algebra, so that L infinity algebra brings extra flexibility. It's just a better, more general notion than DGLAs. And every DGLA L has a minimal model HL. So a minimal model here means that it's an L infinity algebra where the differential vanishes. Now, knowing a minimal model together with quasi-isomorphism between L and the minimal model gives you already full knowledge of the Barmeier-Schroll elements. In fact, they have the same Barmeier-Schroll elements over any local ring, which is great if you want to compute Barmeier-Schroll elements of L, because you just need to know what is the minimal model and compute Barmeier-Schroll elements there. So yeah, this raises lots of questions about minimal models. So what kinds of properties can minimal models have? One popular property a minimal model or a DGLA can have is formality. When do we call a DGLA or an L infinity algebra formal? If there is a minimal model which has vanishing higher brackets. So it has vanishing differential. It also has vanishing higher brackets. The only thing it is has an ordinary bracket. Now, I have a list of examples. So who of you believes that the Hochschild DGLA of a polynomial ring in one variable is formal? Raise your hand. Okay, who believes it's not formal? Believe, expect. Merlin asking some question. What do you mean by believe? What do I mean by believe? Okay, I think, well, okay, so the answer is, okay, what do I mean by believe? I build on your intuition. Maybe some of you have some intuition. And the answer is yes, it's formal, and we'll see in a minute how you can see this. Okay, the second example I wanted to mention is the Hochschild DGLA of smooth functions on manifolds. Well, this is has been super important example to study formality in the past century. It was resolved by Kontsevich in 1997. It's called Kontsevich formality. So these kind of things are also formal. Now, is the Hochschild DGLA of gentle algebras also formal? We will see that this is the case, but first, let us see how you can actually prove such things formal. So how to compute minimal models, right? If we want to show that something is formal, we need to get a minimal model. How to compute minimal models? The first thing you do if you want to compute the minimal model of a DGLA L is you need to find a homological splitting of it. So you split the kernel of its differential into the image part. Recall that the image is always part of the kernel, and you find a complement. So you essentially find explicit basis of the Hochschild cohomology, so Hochschild cocycles. And then once you've chosen that, you also try to find a complement of the kernel, and you call this R. So you need to find this whole splitting in order to do an explicit minimal model calculation. Okay, so there's a few auxiliary maps here. Note that the differential D vanishes on the kernel. So in particular, it maps R bijectively. So R goes bijectively to the image of D. And if you take the inverse map of that, which I've written here, so this is the inverse map of the inverse, you compose with a projection along this some decomposition. This we call the co-differential H. So H is just the the opposite of D on the part of the image. And pi, we call it projection from L to H. Now, if you have defined these gadgets, you can write down formula, which is, I think, due to Kontsevich and Seibelman, for the higher products on your minimal model. And it's defined as sums over all possible trees where you have the things you want to compute the product. So in this case, the higher bracket. So you want to compute a higher bracket of some sequence of elements. And you form all possible trees where at each internal node you put the bracket of L followed by the codifferential, and at the root you put the bracket of L followed by the projection to H. So H is our cohomology. And so you sum over all these kind of trees. For example, if there are 3 inputs, then there's just these 3 trees which I've drawn. So the formula would read like this. Who of you has seen this kind of construction before? Who of you has never seen this construction before? One, okay. 1, 2, okay, thanks. Good to know. Okay. Yeah, so this is how you can compute minimum models. And well, if all these higher brackets vanish, then you are formal. So how does formality look in practice? Let's look at this baby example, which I just told you about. As you know, it's Hochschild cohomology in degree 0 and is concentrated in degree 0 and degree 1, which in the A infinity grading is slightly different. It's just would be concentrated in degree -1, degree 0. This is classically, so where does this come from? This is the center, and this is the derivations on this algebra. Why is it formal? So to see formal, we have to compute the minimum model. Let's look at this. So the whole Hochschild complex degree -1 is all possible curvatures you might be able to add. So all -1 curve chains. And at 0, it consists of all linear maps from Cx to Cx. And okay, so we got to choose a splitting. So how are we going to choose our splitting? So that we first going to split the kernel into the image and some cohomology representative choice. The image in degree -1 is 0 because nothing maps from degree -2 to -1. In degree 0, it's 0 because Cx lies in the center, and the Hochschild differential from -1 to 0 is just commuting, which is 0. And so what we're going to choose is H-1 is Cx, and H0 is the whole kernel, and the kernel is given by those linear maps which are derivations. So if you fix f of x, you know f on all monomials. This is our choice for H. As remainder terms are, you got to choose 0 here because the kernel is everything, and in degree 0 we just got to choose any complement of H0. For example, those linear maps which just send x to 0 and can take any value on all the other powers of x. Now, if you do this choice, you immediately get whichever R you choose. You see that both image spaces vanish, and because H was the codifferential, which goes via the image of the Hochschild differential, H immediately vanishes on degrees -1 and degree 0. So if you look at any tree which takes at least 3 input elements, you got to take at least 1 internal node, and at the internal node you apply the bracket of L, which gives you a degree -1 or degree 0 element, because A and B itself are degree 0 or degree -1, and immediately your codifferential vanishes. So all trees totally yield 0 immediately. So we can include all higher products or higher brackets on HL a 0 in this case. So this thing is formal. So this is kind of easy. Now, how does it work for gentle algebras? Gentle algebras, if we wanted to do minimum model computation here, we first need all Hochschild cocycles, like a representative and a basis for cohomology. How to get this? We already know one specific deformation, right? And we have in fact worked with as many deformation parameters as there are punctures, killing all deformation parameters except one, and keeping and taking that deformation parameter to square to 0. So epsilon squared is 0. You already get as many Hochschild cocycles as you have punctures in your surface. So we already know Q0 many Hochschild cocycles of GTLQ. Now, what are all the other deformations? What are the other Hochschild cocycles? I need to finish within a few minutes. Is that right, Frank?
Yes, that's right.
Thanks. I will try that. So what are the other deformations? For example, what you can do is you can at every puncture, at every incident arc, you can just allow multiple turns around that puncture instead of only one. And you also need to change the higher products, of course. So higher products will be given by orbigons instead of disks. And we were able in my PhD thesis to write down how this works. So you gotta get a full basis of Hochschild cohomology, which looks like this. And you can also, you can also classify the entire even Hochschild cohomology, right? And this is yeah, you get a bunch of stuff. Plus also something which depends on punctures and the number of turns around it. This is no magic. I mean, there's work of Shil Ganratra in the general Fukaya categories case, which predicts something like you get symplectic cohomology, and this is essentially an example of symplectic cohomology. And there's also work in the dual due to in the mirror due to Michael Wang. So this is nothing. It was a tedious computation, but it's not a miracle. But what is maybe interesting is that this thing is formal. How you get to prove that is we introduced a topological grading on GTLQ, which comes from the structure of the surface. Yeah, so you use the topology of the surface to study GTLQ, and it passes down to the Hochschild DGLA. And once you use this topological grading, you can already kick out a lot of higher brackets on the cohomology. You can see very easily that all brackets of at least 4 items vanish. And if you choose R clever enough, you can also show that the 3 brackets vanish. And this way you got that the Hochschild DGLA of gentle algebras is formal. Now, so how to understand this? So if you in a scale from CX, a very trivial example, to Kontsevich formality, this is probably somewhere in the middle, because Kontsevich formality is really crazy with a lot of theoretical background ideas. Okay, so we also classified deformations. So pick a local ring, and what we did is we wrote down for every infinitesimally weighted element of odd Hochschild cohomology, we wrote down an explicit deformation of the gentle algebra. For instance, if we take back our ring, which has as many deformation parameters as punctures, and we take this particular parameter, right? Remember that LQ denotes an element in the odd Hochschild cohomology. You get precisely this thing, the one specific deformation, which we constructed in our first quest today. Now, a theorem we proved is that any deformation of GTLQ is actually equivalent, gauge equivalent, to one of the GTL-RQs. How to go about this? You construct functors of Artin rings, namely this, the parameter space of all R's is an functor of Artin rings in the ring R. The deformation functor is, of course, also a functor of Artin rings, And there's a natural morphism between them, which just maps R to GTL R cube, right? So, phi is surjective on tangent spaces of these functors. Why is it surjective? Because tangent space just means you look over the local ring C epsilon with epsilon squared is 0. And in this case, the parameter space is exactly Hochschild cohomology, which is also, which immediately, and the Hochschild cohomology is also the tangent space of the deformation functor. So with some standard theory on functors of art and rings, you conclude that phi is surjective. Wait, what? This is not normal. Why did we do all these stuff? So why do we prove formality and classification of deformations independently? Just find an explicit L-infinity morphism from cohomology to the Hochschild DGLA. And if you own this morphism, formality and classification follow automatically. Yes, that's true. This would be the ideal world. But it's actually very hard to find these L-infinity morphisms. If you can do this, however, you're very rich. And in the appendix, I sketched an idea how to do this. Okay, the third quest I probably need to cut a little short. Is that correct, Frank? So I want to relate to what Barmeier-Schroll and Wang have done. We recall that we've been working, so what I've been presenting is on punctured surfaces. So in this case, you have fully marked as one boundaries, but not all marked surfaces are of this kind. Some just have alternatingly marked boundary. And if you have an alternatingly marked boundary, the boundary looks something like this. So here are your markings, and here you have boundary arcs, and you're even allowed to choose your arc system free. So you can choose additional arcs if you wanted between the markings, something like this. But you can also choose to kick out certain arcs. And if you know the HKK paper, the idea is to kick out so many of the arcs lying on the boundary, so many boundary arcs that your higher products in the gentle algebra vanish. So in every polygon, you have to have precisely one boundary arc, which is not included in the arc system. And if you do this, you get gentle algebras, which still form a model of Fukaya categories, albeit not punctured surfaces, but Fukaya categories of other kinds of marked surfaces with vanishing higher products. So how to deform them? They are not infinity. They're infinity algebras. Infinity structure is just 0. How to deform these guys? This is a surprise. Keep your eyes open. What Barmeier-Schroll and Wang will show you. Maybe I can take just 1 minute to say something. Deformed mirror symmetry I've done. Well, what did I do? I put these gentle algebra deformations into practice. My starting point was Bocklandt's mirror symmetry from 2011, which runs between gentle algebras and matrix factorizations. And the best thing you could do is try to find the L-infinity quasi-isomorphism between both sides, because if you own this map, you're rich. Please, if you can, compute this map. Now, I have failed to compute this map, but I have, via some construction of Chohong and La, I've computed one specific instance, namely I have transferred to the mirror side the specific deformation GTLQQ, which I presented to you earlier. And yes, so you can describe the right-hand side, so the deformation of the mirror inside this case explicitly. And I have nice pictures in case you want to see that. Thanks for coming, everyone.